What we're going to look at today is a method for evaluating limits. So I've just been letting you work on limits and see what you come up with, but it might be nice to have a method that you can just tackle your limit every single time. So first, you always try and put in a value. If you get a number, you get to stop. It's when you get the indeterminate forms that I like to call warning signs that we have to keep going. So there are actually 7 indeterminate forms. So again, an indeterminate form is a form that tells you we're not done. We have not yet determined the value. So when you see one of these, you need to rewrite the limit. And essentially, you're using any skill from your past in your math to write the limit in a different way. So when we see 0 over 0, infinity over infinity, 0 times infinity, infinity minus infinity, 1 to the infinity, infinity to the 0, 0 to the 0, we need to do something else. So let's talk about those possible something else. First, you might try factoring. An example of this one. X squared minus 9 is the difference of squares. Factors into x plus 3 and x minus 3. That'll allow us to eliminate this term. And then we plug in the limit. So negative 3 minus 3, an answer of minus 6. Why did we have to do this? If we put in negative 3 at the beginning, 9 minus 9 minus 3 plus 3. So there was one of our indeterminate forms. So factoring is very useful. Let's try another one. If you put in 2, 8 minus 8, 2 minus 2, let's try factoring. I hope you remember how to factor the difference of cubes. We say take the cube root of each one of those. That's where the x minus 2 comes from. Then square the first one, square the last one, multiply them together, change the sign. Once you've done that, those will eliminate. We're left with a limit as x approaches 2 of x squared plus 2x plus 4. Plug the 2 in, and we get an answer of 12. So factoring, incredibly important. How else can we change the way a limit looks? We could expand. This one, we'd use Pascal's triangle. We're looking for the third level of the triangle. And when I call that the third level, this is the expansion to the power 0, 1, 2, 3. So our coefficients are 1, 3, 3, 1. 1, 3, 3, 1. And then we have 2, 2 cubed, 2 squared, 2 to the 1, 2 to the 0. X goes the other way, x to the 0, x to the 1, x squared, x cubed. And again, remember, after you've used Pascal's triangle, remember you had another term at the end. Okay, we'll clean that up. When we multiply all these out, the 8s will eliminate, which is why it's incredibly important to remember that. And then we have a common factor of x. You can either just divide everything by x, or if you're happier, pull out the common factor first. It doesn't actually matter how you do it. You'll end up with a limit as x approaches 0 of 12 plus 6x plus x squared. Plug in your 0, and what are we left with? We're left with 12. So expanding is a useful math technique for changing the way a limit looks. What else do we have? We haven't really looked at this one. So a conjugate comes in when you're working with radicals. A conjugate is simply the exact same thing as the expression with radicals, except we change the middle sign. Middle sign was negative. Middle sign is now positive. And if you multiply the top by the conjugate, you must multiply the bottom by the conjugate, because then essentially we're just multiplying by the number 1. So it'll look different, but we're not changing it mathematically. Okay, let's expand the top. We're taking 3 plus x under a root minus root 3 by root 3 plus x plus root 3. So we have the numerator and the denominator. When you multiply the radical by the radical, those get eliminated. Root 3 by root 3 plus x, there it is. minus root 3 by root 3 plus x. That cancels with that one, which is why we're multiplying by the conjugate. So the whole point of changing this sign was so that we would get these two terms that we can then eliminate. That's why the conjugate is useful. The last term comes from minus root 3 times root 3, so that's minus 3. So look what happens. We've multiplied by a conjugate and gotten rid of all the radicals in the numerator. Now the bottom, save yourself some work. Don't expand. Just put the x down and put the root 3 plus x plus root 3 down. What can we do now? This is useful. So now we have x over x times root 3 plus root 3, and the x's will then go. So that's why it was really useful not to expand, so it was obvious that the x was common. Okay, what do we do now? We're plotting 0 in for x. What does that do for us? We get 1 over root 3 plus root 3, which is the same as 1 over 2 root 3. So let's just look at this again, because this is the first time we've done this. You multiply by a conjugate when you see a sum or difference of radicals. The conjugate is the same thing with the middle sign changed. Why we change the middle sign is so that this term can get eliminated. We multiply it out, cancel any terms that we can. We should have a common factor of x left that we eliminate. Then you plug in your limit and get your answer. Common denominator, we've seen this one before. What is your common denominator for all of these terms? Your denominators are 3x and 1, so your common denominator is 3x. When you multiply by that, what are you left with? When you multiply by that, what are you left with? And leave the bottom factored. So 3x times 1 over 3, we're left with x. 1 over x times 3x, we're left with 3. We can then eliminate those, keeping in mind that when you divide, that goes in once. So 1 over 3x, 1 over 3 times 3, 1 over 9. So when you see fractions, multiplying by a common denominator will help. Dividing by the highest power of x from the denominator. We did this when we were approaching infinity. Keep in mind, it only works when you're approaching infinity. And generally, you need a fraction. Highest power of x from the denominator is x squared. So we're going to divide everything by x squared. Clean it up. You can reduce those. You can reduce those. You can reduce those. And that's about it. As x gets very big, what is 3 over an enormous number? What is 1 over an enormous number? And hopefully you're comfortable with that now and say 3 divided by a huge number is approaching 0. 1 divided by a huge number, approaching 0. So we're left with 5 over 3. So dividing by the highest power of x from the denominator works when you are approaching infinity. Now occasionally, you're going to try all of those 5 methods and go nowhere. So here's the last thing you're going to have to do. You're going to have to think about this. So I'll give you 2 examples. Let's approach infinity. 3 minus infinity is going to be minus infinity. How do you evaluate a negative exponent? We put 1 over 7 to the infinity. If you're unsure of what just happened, how do you evaluate 2 to the minus 3? That's 1 over 2 cubed. When you see a negative exponent, it means you're dividing by that many. So 7 to the minus infinity, 1 over 7 to the infinity. What would you get if you raised 7 to the power infinity? 7 times 7 times 7 times 7. Ooh, it's going to get really big. And 1 over an enormous number is 0. Fair bit of thinking involved. Let's try another one. We've talked about dividing by the highest power of x, but this is different. Well, let's plug in the limit and see what we get. 2 to the infinity. 3 to the infinity. Okay. That's a warning sign. We need to try something else. Is there another way of writing this fraction? The 2 is to the exponent x and the 3 is to the exponent x. Ah, that's the same thing. How does that help? If you were to take 2/3 times 2/3 times 2/3 and you do that again and again and again, we're going to think of this by looking at your pencil. Imagine sharpening your pencil so that 2/3 of it is left. And then you do that again so that 2/3 of it is left. And then you do that again until 2/3 of it is left. And then you keep doing that so that you're only left with 2/3. That's what happens when you multiply by 2/3 again and again and again. And eventually, what happens to your pencil? There's nothing left. So when you multiply by 2/3 again and again and again and again, you end up with nothing. You just get a value that's smaller and smaller and smaller. You might want to think about what would happen if it was the other way around. What if it was 3/2 to the infinity? What would happen then? Three over 2, 1.5. So that would be like saying I have a starting salary, and every year I get that much plus half. Looks like our salary would get bigger and bigger and bigger and bigger. Oh, there's another way to do this. You can think of the exponential function, 3/2 to the infinity. What would you approach there? Looks like that one would go to infinity. So smaller than 1, we get smaller and smaller and smaller, approaching 0. Bigger than 1, we get bigger and bigger and bigger, approaching infinity. So be prepared to think. So let's recap. Step 1, you're substituting in the value. If you get a number, you're done. If you get one of these, you know you have to do something else. There are lots of something else's. I'm going to start at the end of the something else's. How do we know when to divide by the highest power of x? That works if you're approaching infinity. So if you see infinity and often a fraction, that's when this is useful. Common denominator, that's when you see fractions. Conjugate, that's when you see radicals. Expanding, that's when you see brackets and exponents. So there's lots of clues as to what to look for. So when do you do factoring? Essentially when you don't see anything else. Not infinity, not fractions, not radicals, not brackets and powers. So then we try factoring. And then if nothing else works, that's when you're going to have to think. So I'm hoping that having a method for evaluating limits will allow you to go back and look at any questions you were stuck on and say, is there something here that would help? Do I see infinity? Should I try dividing by the highest power? Do I see fractions? Should I try multiplying by a common denominator? Do I see radicals? Should I try multiplying by a conjugate? Do I see brackets and exponents? Should I try expanding? Do I not see anything but recognize factoring, difference of squares, difference of cubes? And if nothing else works, just thinking about it help me work out the limit. So I don't have any particular exercises for you today. What I'm going to recommend you do, go look at all the previous exercises we've done. If you had any questions that had you stumped, see if this method helps.